Today's topic is axial tension and compression. We'll go through 3 statically determinate examples. The first one. A 2-stage rod has been permanently fixed at end A and loaded with forces, P and 2P as shown in the figure. Calculate the reaction at the fixed end and the diameter of both rods. If the stresses in the rod cannot exceed 60 megapascals, tensile strength, and 80 megapascals compressive strength. Draw diagrams of internal forces, normal stresses, and rod elongations and displacements. And the force P is given, which is marked in the figure. Young's modulus is given and dimension A, which describes the length of the rod, is given. The first thing we'll do is sum the projections on the x-axis, and from that we'll immediately calculate the reaction at the fixed end. Forces whose sense of direction is in line with the adopted x-axis, that is, forces whose sense of direction is the same as the sense of direction of the x-axis, are positive. If it's directed opposite, they are negative. So the sum of projections on the x-axis equals 0. Positive RA, add 2P. Minus P equals 0. From this we calculate RA, which is equal to minus P. So we've already calculated the first thing in the reaction at the fixed end, which is equal to minus P, that is minus 10 kN. Next, we'll write down the forces in the successive sections of this rod. So we have 3 characteristic sections here. A characteristic section changes when either the rod diameter changes, like here, or if a new force is added, like here. So we have 3 characteristic sections here. The force in the first section, looking from the right side, is minus P. Minus P, that is minus 10 kN. The force in the second section is also minus P. We don't see this 2P yet. We only see it here, where the characteristic section changes. That is here where the force is applied. So even though it's another section, the force in this section is the same. And the next section is because the diameter has changed. The force hasn't changed. So also minus P minus 10 kN. And in the third section, we see all 3 forces, so we have minus P, add 2P, so positive 10 kN. And the strength condition is that the stresses, for which the formula looks like this, N divided by A must be less than or equal to, and now, depending on whether a given section is in tension or compression, these stresses must be less than or equal to the tensile strength or compressive strength. And for sizing, for checking strength conditions, we take the absolute value. And now, which part of the rod is compressed and which is stretched? Well, the first and second parts of the rod are compressed because the force in the rod is minus 10, negative. So this part is compressed and the third part is stretched because the force in it is positive P. And now for the strength conditions we take. Well, we want to check for maximum stresses. So even though there's compression in these 2 sections, the stresses will be higher in the first section because the cross-sectional area is smaller. So if we apply the same compressive force on a smaller cross-sectional area than on a larger one, the stresses are higher on the smaller cross-section. So we take the first section for compressive strength and the third section for tensile strength. So the compressive force, its absolute value of the compressive force is 10 kN, kN, so times 10 to the third, divided by the cross-sectional area expressed here as the ratio of A and 2A. So the cross-sectional area of the first part is A, must be less than or equal to the compressive strength, which is 80 megapascals, so times 10 to the sixth. We transform it, multiply by A, divide by 80 times 10 to the sixth, and calculate A from this. We do the same with tension, so we take the force, its absolute value, also 10 kN divided by the cross-sectional area of this part, which is 2A, less than or equal to the tensile strength, which is 60 megapascals. We also calculate the cross-sectional area from this, that is 2A, and it's 833 times 10 to the minus fifth. So that we have expressed the same way these results, I moved the decimal point 1 place to the left and write it as times 10 to the minus fourth. Now we can directly see which value is larger and which is smaller. If someone had doubts, and we take the common part of these intervals as our result, that is, so A must be greater than or equal to 1.25 times 10 to the minus fourth square meters. We need to size the diameter. So the area of a circular cross-section expressed by diameter is PD squared fourths. So this sized area of ours, pi d squared fourths, must be greater than or equal to 1.25. And from this we calculate d. So we multiply by 4 over pi and take the square root of the result. So we calculate the diameter. It must be greater than or equal to 0.0126 meters. And if we round it up a bit, because it has to be greater than or equal, right? And to be safe, we round it up slightly. So we can assume that the diameter is equal to 0.013 meters. We can already calculate the cross-sectional area on this size diameter, which we will take for calculation. So for stresses and for rod elongation, so pi d squared fourths gives us the cross-sectional area on the size diameter. And now we can calculate the stresses we have in these 3 sections of ours. So stress equals force in the rod divided by the cross-sectional area. And now we're not taking the absolute value, but the actual value. In the first section, the force was minus 10 kN, so we take it with the sign, divided by the cross-sectional area. And we get, well, if we enter it as it's presented here, we get a very large number on the calculator, right? And it needs to be multiplied by 10 to the minus 6 so that we have megapascals. Because when we substitute everything in basic units, we get the result in the basic unit, that is, in pascals. And we write it in megapascals, so the result times 10 to the minus 6 again. We have minus 75.36 megapascals. The same with the second section. Now the cross-sectional area, which is in the second section, so 2 times A. We have minus 37.68 megapascals. The force in the third section is positive, so the stresses here are also positive. The same as in the second section, just with the opposite sign. Okay, so now we can calculate the elongation. The formula for elongation is force in the section times the length of this section, divided by Young's modulus and cross-sectional area. So we'll calculate the same way in the first, second, and third sections. So we take the force from the first section, the length of the first section, Young's modulus is constant, and the cross-sectional area of the first section, then the second, and so on. Here we also take actual values, not absolute ones, because this determines whether we'll have shortening or elongation of this part of the rod. If the force is negative, then shortening occurs. So everything in basic units. 2.1 was given times 10 to the 5 megapascals. So you have to be careful, it's 2.1 times 10 to the 11 pascals. We get such a result, minus 7.18 times 10 to the minus 4. If we multiply it by times 10 to the 3, we'll have it in millimeters. So then it will be 10 to the minus 1 millimeter. And if I move the decimal point once more to the left, it will be without exponential notation. That is 718 thousandths of a millimeter. Well, I wrote it out so long here exceptionally. In the next examples, in the next calculations, I won't write it out step by step like this. Just simply. So the force in the second rod, the length of the section, the cross-sectional area of the second section. Well, and the same, we substitute the values and calculate. The same with the third section. Well, and we have practically everything we need to draw the diagrams that we were asked for in the task content. So we write out the forces in individual rods, and we draw a diagram of normal forces. So in the first section, it's minus 10. In the second section, it's also minus 10. In the third section, it's positive 10. The diagram is step-like. We write out the stresses and draw a stress diagram. The diagram is also step-like. In the first section, minus 75.36. In the second, 37.68. In the third, the same, but positive. We write out the elongations of successive sections, that is first, second, third, and the diagram is also step-like. And now the displacement diagram. The displacement diagram won't be step-like, but will be linear. We start drawing from the fixed end. Here the displacement of the fixed end is equal to 0, and it changes linearly. The displacement of the third part, here was the first, second, third, so the displacement of this cross-section is simply the elongation delta L3, that is the elongation of the third part. So from 0, we go towards the plus side by about 179 thousandths. It changes linearly. The displacement of the second cross-section, this one here, is the sum of elongations delta L3 and delta L2. So delta L3 plus delta L2, well, that will be 0. So from 0 to 179 thousandths. And then we subtract this value again, 179 thousandths. And we're at 0. And the same. Then we sum up, we add this value of 718 thousandths. So from 0 here, we go towards the minus side by 718 thousandths. And this is the displacement of the first cross-section here. That is the end of the rod. The displacement of the rod end is the sum of these three elongations. This is how it looks, and the diagram is linear, not step-like like the previous three. Well, and that's everything they asked for in this task. So we move on to the second task, to the second example in the next video. If you have any questions, please write them in the comments below this course. See you in the next video.